Okay, let's go ahead and get started. Our speaker today is Dan Quinlan from Lawrence Livermore National Labs, who has been working for quite a while on an infrastructure for translating C source to source, and as a result has a system that he can use for lots of different things in the middle. Code analysis, optimization. People have done instrumentation things with it, all sorts of stuff. So with that introduction, I'll send you off to him. He's going to talk a bit about the system. He has a postdoc here with him who's going to talk a little bit about some software engineering things that he's been doing with it, and we hope to have a bunch of time for questions.
Thank you very much. So ROSE has been a project that we've been doing for quite some time, and it was originally focused on the optimization of user-defined abstractions. The motivation for this was that we had, at the lab, developed numerous high-level object-oriented abstractions and libraries of abstractions and frameworks to support the development of scientific applications for computational fluid dynamics, but there were issues associated with the performance of this. And at a DOE laboratory where they're very obsessed with performance, you have to get all these details squared away. And so we started ROSE as an attempt to address the performance optimization of user-defined abstractions. In doing so, of course, you have to develop the whole compiler infrastructure for supporting this. But we were obsessed with the idea of presenting having an audience, which was library writers, not compiler people. So that's a little different than some projects. And two, we were interested in representing the full detail of the C++ language. Now, we sort of get C for free. We've also been pushed for a variety of reasons from our funding agency to also support Fortran. But the point is that we can represent the full representation of C++, every little detail essentially that is in the source. We can represent that, and of course, make it available for automated tools to be built. ROSE is not a magic bullet that you run over your code to do one thing in particular. It's a tool for building tools which are source-to-source translators, which of course do whatever it is you say it should do when it goes over the code. I'll explain a little bit about just how ROSE is organized. Thomas, at the very end, I'll basically try and give a short talk and then allow Thomas to talk for 10 minutes on some of the work and how he's using ROSE for reverse engineering of codes. And hopefully we'll have lots of time for questions. So let me also say that I have a example tutorial. If anybody's interested in just thumbing through it, I'll be happy to actually just let that be passed around the audience. So you can look at that if you like. Please make sure I get it back when it's all done. But the table of contents gives you a rough idea of the 60 or so different examples in there of little tiny translators that literally go do different sorts of things. Some of them are intended to be instructional to help users learn how to use ROSE. Some of them are there so that when I get the certain questions asked for the 50th time, I can say it's in the tutorial. And others are there as simply examples of things that we've done with different companies and different research groups that were things which they needed to be done and which I asked if I could put in the tutorial. So the motivation for this work is that Department of Energy develops huge amounts of software, not just in C and C++, but also in Fortran, hence the necessity of us addressing Fortran. The Fortran work is currently a collaboration with Rice University, and it's not available yet in the ROSE distribution. We have about 2/3 of it in place, and another third of it has to be delivered. But we've been addressing the analysis and optimization of C and C++ applications, specifically scientific applications. And so some of the optimization that we've done has been those things that are important for scientific applications. Lots of loop optimizations, for example. But a lot of custom tools could be built using this. We're not exactly in the business of building custom tools. We're more focused on optimization. But ROSE is a general infrastructure supporting a lot of different sorts of tools. It's a source-to-source approach, which means that a translator built using ROSE takes in source code and it outputs an executable. Now, it's source to source internally, but internally we're going to hand it off to the vendor's compiler, and the vendor's compiler is going to compile that generated source code that we generate and generate an executable. As a result, in a large makefile system for a large project, million lines, thousands of files, you can simply change the name of the compiler to the name of the translator that you've written and analyze your source code. It's meant to be very simple, and it works in this context, and it's necessary that it be designed in this way because we simply have large million-line applications with thousands of files at the lab, which we have to be able to work with. And actually, we want to not change their makefile system one bit because it makes the source code look simple. Makefile systems are the most complicated things I've ever seen. But the point is that there are a number of different stages, intermediate. We use the EDG C++ front end internally. We have a research license with them that allows us to distribute a binary for research use only. And we have access to all the source. And we routinely share the source with those who have an EDG research license. But we can also just give away the binary. The next stage is that we translate it internally to an internal representation, which is more friendly to being modified and examined using automatic tools. And we also have mechanisms for recognizing high-level abstractions, automating that. One, you insert this part. That is to say, we have a lot of different analysis built in internally. We have a lot of different transformations. But if you have something that you want to do, some specific type of analysis or some specific sort of transformation, you contribute this part. There's no free lunch. After you've done that part, we then pass it through to generate source code. We then pass that optimized source code on to the vendor's compiler. I'll show you perhaps an example, or there's examples in the tutorial that basically show that the code we generate is generated with all the source code, all the comments, all of the preprocessor control structure. It looks relatively pretty, I think. But the point is, we save all the information about the source code. Yes?
If you're using EDG, do you support all the GCC extensions?
Yes, and even some of the ones that they don't support. There's a lot. Though, honestly, if I were to use the latest version of EDG, perhaps they would have fixed some of these, and I wouldn't have to do some of the work that I've had to do. But yes. We're using 3.3 right now internally, and there's 3.7 that is, I believe, available. And I could upgrade it if it's ever important, but we're using 3.3 right now. So Rose is a tool for generating tools that would operate on source code. We take in the source code, we generate an AST, we then manipulate that AST to form a different AST or modify it in some way. The properties of this AST is that it's object-oriented and it's easily modified. And then we generate source code. It's very simple. Yes?
EDG doesn't have a Fortran front end.
Yes, we don't use the Fortran. We don't use that Fortran front end that doesn't exist.
Right. So the question, of course, is which Fortran front end do you use?
We use the Open64 front end. We have as part of a contract with Rice, who has a lot of experience with Open64 Open64 compiler. We have a contract in place that has allowed them to generate a whirl, which is the intermediate representation of Open64, to Sage 3, which is our intermediate representation, and that translator is in place, and that gives us roughly a Fortran 77 level of capability, is my understanding. I have yet to get the front end. I have the IR node modifications in place, and I have the back end code generation in place right now. So this has been work that we've been doing with them for quite some time, and I want to make sure that they get credit for that. But as a result of that, we expect that eventually we will be able to step up to the Fortran 90 capabilities of that compiler. However, to the extent to which that compiler doesn't address maybe Fortran 95 or Fortran 2003, we're pursuing other opportunities to perhaps see if there's other front ends that might be more appropriate. But that's not very important to us. We're trying to first get a base level of Fortran 77 level capability, much as earlier on, we first got a level of C capability before moving on to C++, which wasn't supposed to be that hard, but really was. Yes?
Based
basic question. Are you only looking at one source file at a time, or can you deal with groups of source files?
We can deal with groups of source files. You can either specify all the source files on the command line, but that becomes pretty damned impractical when you get to 1,000 separated over 100 different directories. We also have a persistent mechanism for storing analysis information, any analysis information that you want, any information you want, into a SQLite database that can be retrieved afterwards. That's a mechanism by which we build call graphs over big number of files if the SQLite database is used in the configuration. And there's also whole program analysis work that we're doing, which I'll explain in a moment, which is designed at being able to read in or process all of the files separately and then collect them together such that we can hold 1 million lines, 5 million lines of code in memory at one time. And so the next reasonable question there is, how much memory does it take to hold 1 million lines of code? Well, about 400 megabytes right now. So that's a fairly reasonable. Basically, memory sizes have gotten so large that I think it's entirely reasonable, though the complexity of the analysis is not reasonable. The storage of of an entire application in memory is quite reasonable using the mechanisms that we have. We're not as large as GNU, for example. So there's a variety of different program analysis and optimization capabilities that are available built into ROSE right now. There's call graph analysis. There's resolution of function pointers to restricted subsets of functions, resolution of virtual functions, and of course, the combination of the two, pointers to virtual functions, which is really obnoxious. In order to support that, we have to read all the files, we have to build the call graph hierarchy, and then we have to do the analysis on all of the accumulated information. SQLite is used as a mechanism for storing this information. An alternative, which we expect to be able to use in the future, is to simply do it in memory, simply because we'll have the entire application in memory as an alternative. But we've had to use and maintain these mechanisms for processing things one file at a time, simply because that's where we've stood in being able to process large codes so far. We have dependence analysis. It's procedural, it's not interprocedural. There's control flow analysis. These are examples, by the way, that are in the tutorial. I forget what chapter control flow is, but there's a little example of how to, in the tutorial, of how to build a control flow graph. And it shows you the functions you have to call in order to have that be done for you. And then there's an example of a arbitrary source code, which I've simply chosen mostly at random. And what we do in the tutorial, and there's a tutorial directory of examples also, what we've done in the tutorials is literally take that source code, present it in the tutorial, take that input code, present it in the tutorial, compile the example code, run the input code on the example code, take the output, put that in the tutorial. So the tutorial represents the current state of exactly what's working, or in some cases not working. So there's none of that in the tutorial right now, at any one time. We have slicing. That's very important for certain sorts of analysis. There's partial redundancy elimination. Some of these things are contributions from people who've worked with us. Partial redundancy elimination, for example, is a contribution from Jeremiah Wocock. Connection to the Open Analysis Framework is Open Analysis Framework is a framework being developed by some friends of ours at Michelle Stroud at Colorado State. It's intended to be an IR independent analysis framework, and so we've been using that as well. And Argonne has been using ROSE with that as well. I'll show at the end a list of about 24 or so different groups that have been using ROSE worldwide, and some of these contributions have been as a result of collaborations with them. We're very big on collaborating with people. That's one of the ways in which we test our own work and also get contributions from others. There's a number of different optimizations in place. The optimization work is a result of Ching Yi's work, who was a postdoc with us for almost 3 years from Rice. And she put her thesis work into ROSE. As a result, we have rather sophisticated levels of loop optimization, fission, fusion, blocking, unrolling, array copy, etc. There's also inlining and outlining capabilities. There's research work that we're doing on annotation-based optimizations. The point here being that user-defined abstractions have certain properties. It might be that you've designed a particular class which has no aliasing associated with it. It's a part of the semantics of that class that it has no aliasing. you have no way of communicating that to the compiler, and because the implementation has a pointer inside of it, the compiler is going to turn around and not do a lot of things because it doesn't know it could be aliased. But you know that it couldn't be aliased. So you could annotate abstractions in order to communicate this sort of information, and as a result, enable certain sorts of optimizations. This is some of our research work, but it's very much in line with research work that we're doing on customized optimizations. So there's been a number of accomplishments for us. Robustness has been a very important issue. We are the only compiler group at a DOE lab that I'm aware of, though DOE does fund other academic compiler research. As a result of being a compiler group at a lab, we have to compile lab applications, which means that they test whether or not we're worth anything at all by throwing us 1 million lines of C++. So I'm pointing at a couple different applications there, and these are applications at the lab that we can compile, and applications that we're currently developing specialized analysis and have written in the past some specialized analysis in order to do certain sorts of optimizations, and I'll be discussing that just a little bit. Separately from that work that we're doing internally, our goal is to, notice that rows, for example, is on the list. There's about 3 or 4 bugs that are keeping us from compiling rows with rows itself. So sort of let you know where we stand. Rows itself, about 1 million lines of code. We're trying to step up to about 10 different million-line applications before we release rows this summer. This is going fairly well. I get a lot of help from other people in helping find problems. But in general, I'm the bottleneck to getting them fixed because I have to debug them. There's collaborations that we have with IBM that we're very proud of. This is IBM Haifa in Israel. They're developing tools using rows for use internally at different sites at IBM. Yes?
Some of those applications are capable of running on multiple machines, right? Does rows understand the inter-machine communication at all?
What app? You're referring to parallel applications?
Yeah.
Okay, so that's a very interesting question. The reason why it's interesting is because, yes, all of the applications at the lab, scientific applications, are parallel applications, and they don't just run on a couple different machines. They run on machines with thousands, tens of thousands, 64,000, 128,000 processors. These are very large machines, but they are codes that are essentially serial codes with embedded communication that makes them parallel. With rows, we can go and see where the embedded communication is, but there's nothing parallel about rows. And the ability of rows to recognize the use of a parallel abstraction from a parallel language library like MPI or something like that, parallel message passing library, excuse me, is simply the same mechanisms that we have for recognizing all abstractions. And so, yes, we can go and find where MPI is being called in a large application, and that might be very interesting, but there's nothing about the compilation of a parallel code that really makes it look any different than a serial code. So in a sense, it's a serial issue. The compilation is a serial issue. Now, we could turn the analysis, if it's sufficiently expensive, into a parallel issue. Now, that might be fun, but that's a completely different subject. So there's a lot of different custom analysis that we're doing. Analysis to find properties in the class. So for example, there was one application that loved static initialization. They thought it was very good. They used it everywhere. Then they changed compilers and realized that maybe it wasn't so good after all, because its order of static initialization is compiler dependent. So they promptly removed it. And that went great until they had a bug, and then they discovered, oh, the whole bug, that particular bug, was a result of static initialization. But they thought they had removed it all. It turns out it's rather difficult and rather subtle to detect all the places where you've built a static something or other in a class that's going to cause a problem for static initialization. So after several months of, they thought they'd found the last one last time, yet they had another bug, and they traced it down to this particular problem. I was asked if I would go find the latest one. So I asked them to not tell me where it was, And I would go write a special tool that would go over their entire code and find it. I found 9 of them. There were false positives as a result of an internal bug in rows. I fixed the bug, so this is the value of us working with these groups. I fixed the bug, and we found that one of the 9 was in fact the one that they had just fixed, and we verified that there weren't any more. So that's good. The point is that you may be in a similar situation where, for a completely different reason, there's something in your code that you used to like a lot, and you discovered that you don't really like it so much anymore. And you might want to find where it is. And it might be completely legal C++, but you still want to find it and kill it. So that's an example of how that's done. There's work that we've done on loop classification. Loops in scientific codes come in many different varieties, and there's all sorts of opportunities to optimize certain types of loops. And so we've done work on loop classification for a particular application at the lab. We've also been doing work for more complicated, each of these become a little bit more complicated and more involved. We've also more recently done work looking through a large million line application, looking for where it is 2 functions could be inlined, and where it is there's a loop that could be fused as a result of that inlining. Inlining is something for which you're never going to get the vendor compiler to do it, because typically alias analysis prevents it. And we have more sophisticated mechanisms for doing that. And so as a result, we could do fusion if we could see things together. The trick is, how many opportunities are there in a million lines of code to do fusion of 2 particular loops and fuse do fusion of loops that are across different function boundaries. So this is a specialized sort of analysis written just for optimization of scientific codes. Yeah, well, there's other things too.
How's the IBM work? How is that going to be like re-released under the licensing with EG?
Well, they have a worldwide license to use EG.
But are they going to be able to give that back to you guys?
Yeah, sure.
Are they going to have to get it?
You might have to pay for it. Actually, it's the third example in the tutorial at the end of examples of how to do code coverage. There's a code coverage chapter on there. I asked them when I wrote it whether or not I could include it in the tutorial, and they said, yeah, sure, no problem. And so, I worked with them to write it, and as a result, there's a code coverage example there. That's most of the work required to do code coverage. Now, they've added more work, and there's a tool which they run with that to interpret the results, and that's the part that they make actually available for free on the web, but which maybe for research only or something. I don't know. I don't know what the rules are regarding it, or it may be that it doesn't work on some particularly large problem or something like that. But these are tools which they're using at different worldwide sites for detecting bugs in threaded applications, and the code coverage is just one small part of the problem. So actually, this is part of research work that we're doing with them on detection of bugs, automatic detection of bugs. They've been doing work on the automatic detection of bugs in threaded applications for some time, and they've had great success with this. The basic technique is you instrument the code, and you perturb the thread, perturb the order of the threads when they execute, and you do a code coverage to make sure that you've covered everything, and you detect things like there's a shared variable here, but you've only ever shown us an example of it being used by one thread. So as a result, maybe it doesn't have to be shared, or maybe you need better test coverage in order to bring out the problems that might be apparent if in fact it was shared across multiple threads. So the point is, they detect many, many subtle bugs in threaded applications, but they had previously done this with Java and had no access to C or C++ in order to do this. And as a result, working with us, they can have access to C and C++ and source code instrumentation. What we have is actually more powerful than we would need to a certain extent, because we're not trying to do optimizations, etc. But it's been very useful. You might ask why this is being changed. So ask me separate more questions about that. So there's all sorts of interprocedural analysis that we're involved in regarding loop optimizations. I won't cover that too much. I talked about it briefly. There's work on empirical optimization. Empirical optimization is the technique whereby on a particular machine, I don't know what is the combination of optimizations that will make the most amount of difference, but it's probably different for each machine. And here I'm showing loop fusion. Here's the unfused loops. Here's the fused loops. And what we're looking at is a particular hyperbolic, piecewise parabolic method implementation with 50 different loops. And we're going to generate all the different possibilities of pairs of loop fusion. Actually, not pairs of loop fusion, of loop fusion. But we're not doing any reordering, because that would make it very expensive. As it is, there's 128 different possibilities. There's a lot more if you allow reordering. The point is that we can write each different version of the code, run it, and see what the performance is. The performance in this case is measured in 2 different ways, which I'm not going to go into. But this is work that we've been doing with people, with Ken Kennedy at Rice and one of his students, and Qing Yi, who was a postdoc with us, who's now at University of Texas, San Antonio. This is a simple example of loop optimization. People write code like this for clarity, but you might want it to run like this in order. You might want to have be generated this code for actually running it, because this code will be factor 2 times faster than that code. The compilers will not typically be able to fuse those sort of loops, but we can do a lot of this sort of stuff. This is an example of a 2D case, simply showing that it gets more complicated. People tend to write code so that they can be maintained. So this limits the sorts of optimizations that they'll introduce by hand. And yet we can turn around and generate equivalent, much more complicated code, which you wouldn't want to maintain, but can be automatically generated for you and is much faster. In this case, we're showing different sorts of relaxations, which are typically actually expressed as separate loops when they're written by hand, but which can be fused as a result of loop fusion and skewing. And as a result of that, you can get a factor 2 improvement in performance. But you'd never want to maintain this stuff, because it's very difficult. It's an example of where it is code should be written by hand, or code written by hand should be written to be maintained, and code generated internally can be written for performance. Yes?
You talked about the performance gains. So is that for the massively parallel machines that you're talking about before? Does that also apply to x86?
It makes no difference. I'm talking about serial performance here. Parallel performance would be equivalent, but I'm not talking about parallel execution. We can talk about parallel execution all you want, but this is just serial stuff.
But does it apply to...
And it applies to parallel as well.
Does it apply to Intel processors?
Yes, it applies to Intel processors just as much. And the reason why is because you're essentially, ask me afterwards, and we can really cover why that makes a difference, and why it's really quite processor independent issue, simply because you're increasing the locality of the computation. And that locality, that increase in the locality of the computation is good for all modern processors that use a cache. So it's just as good for Intel as it is for other processors. This is work that we're doing on automatically recognizing high-level abstractions. Here's a little tiny example code. It's written using a couple different abstractions, a range object and a double array object. These represent array objects, multidimensional array objects is C++. And here's a little tiny expression involving those abstractions. So here what we have is the AST, and what we have are the different markings for the different pieces of the code. So for example, the blue represents the array abstraction, and the green represents the range object. So what we see is that there's range object, array object, and then there's the big expression involving them. And at the leaves of the expression tree representing the expression there, we have the individual index objects. And in white, what we have are the +1s representing the C++, which didn't correspond to any one of these library abstractions. The point is that we can automatically read an application, read the libraries from which it was used, and mark the AST to have all this information, so that when you want to go do optimizations and you just want to find all of and you have a particular optimization that you just want to do on, for example, the use of array abstractions, you can easily find them. So that part can be automated. One of the things that we've also done is we've hooked up performance information so that you can get performance information in the AST also, so it tells you something about whether or not it's even relevant to do certain sorts of optimizations there or not. This is the slide that I was referring to a moment ago when I was talking about reading in the applications separately. Here we have 3 different ASTs for a little trivial program. Keep in mind, Rose works on million-line applications, but they don't fit on the slides, so I represented really trivial things on the slides. But here we have 3 different applications, 3 different files, and what we can do is we can turn around and merge those together so that the analysis of each one, nothing has necessarily changed, but we've essentially represented them more compactly. The principal issue here is that a million-line application at the lab is typically 1,000 files, each file containing about 1,000 lines of code with 75,000 lines of header. And I don't have room for that 75,000 header to be replicated 1,000 times. So this makes it very space efficient. And this is a necessary technique for representing huge applications in memory at one time. Now, once we have it in memory, we can do all the same analysis that we could do or that we would write for an individual file. We can simply do it on the whole AST. This is a somewhat trivial example of a call graph. It's not a very big one, but obviously it's a little bit bigger than 3 or 4 points. Each one of these black dots is a function. Each one of the blue lines is in fact a line between the functions, which is a function representing a function call. This is actually represented using a tool that Thomas will talk about in a little bit. But the point is that this is a call graph showing what function's calling what. And in fact, actually, because of the scale of it, it doesn't tell you anything really. But it does tell you that there's a little group of functions over there on the corner which aren't called by anybody, and maybe they don't even need to be there. But this is some of the work that we're doing to step up the current work in the call graph analysis. This is another sort of tool and capability that we've built into Rose, specifically the ability to combine Maple with Rose to do symbolic manipulation. In this particular case, what we're doing is we're counting up, we're basically annotating the AST with modeling attributes. These modeling attributes are saying that there's a memory access here, and we're basically counting up the memory accesses. So we count up the memory accesses, we get an equation for this memory access in terms of B, and then of course we end up, in terms of bound, and of course then we get another one in terms of bound. So we have generated an equation which represents the complexity of the computation in terms of the, an equation which you can compute. And in this particular case, this function's calling foobar. So main here is a summary of the complexity of main, taking into account the complexity of foobar being called in an order n squared operation. And foobar has its own complexity, and so on, so on. At any rate, you can automatically do this ad nauseum and end up with information about the complexity of the code. Here what we're doing is we're representing a graph of the complexity. This is a graph of the complexity of main, and I believe this is a graph of the complexity because main actually depends upon only those two variables, whereas the complexity of that function depends upon a couple more variables, and so it ends up being a more complicated representation. But it's what you'd expect. It's quadratic. Here's a very nice example as a result of collaboration with people at UC Davis. This is the annotation of types with unit information, the sort of stuff NASA really wished they had about 10 years ago. The point is that alpha, for example, is specified to not have any units. Some of these variables are specified to have units. So, for example, this density is kilograms per meter squared, per meter cubed. Thickness is in meters. Energy is in meters squared, kilograms per second squared. And the point is that by annotating the variables in a few places, what can be done is through type inference, one can interpret what the types are of these things, and in the process determine that there's a bug here, specifically right here, because one knows that the exponential, the value which is exponentiated is unitless. there's a theorem of this, and also, of course, it doesn't make any sense for it to have units. But in order for that to be units, we have to get meters to cancel with what x0 is, and x0 is computed using this, which is evaluating that, and this is using information about atomic weight, atomic number, etc. The whole point is that this should have been a reciprocal. But what was able to be determined was that there was a bug. Now, the exact fix of the bug, who knows? But the point is, this should have been a reciprocal. And if it was a reciprocal, then it would have been fine. This sort of analysis, at static analysis, in order to find bugs is very interesting to us, which is why it is we've been working with these people. This is Ling Xiao's work, who's a graduate student at UC Davis, and Professor Zedong Su is his advisor. And this is a result of collaboration with them. This is a capability that we're trying to stand up in ROSE in order to look at scientific applications. A very large one, of course. The most common question I get, which I haven't got yet actually, is what does my output look like when I run it through ROSE? The most common thing that happens that people are used to at the lab is that if they hand their code to a tool, the output of that tool will have seriously deranged their code, and this upsets them a great deal. Here I'm showing you an input code, and here's the equivalent output code. There's very subtle differences between the two. Other codes would give you a little bit more difference. The tutorial shows you some other examples of what the input looks like, what the output looks like. But basically, I'm saying that we preserve the comments, we preserve the preprocessor control structure. There's an awful lot of stuff that's preserved. We save all the information about where every construct began, both in file name, line number, and column number. So it could be reconstructed even better. But the point is, and there's mechanism, and there's a particular example where it shows you how to change and tailor the construction. But the point is, we go to great trouble to output the code in a reasonable way. So these are the sorts of interactions that we have with different groups. Specifically, there's internal lab interactions that we have. There's work with other laboratories. Argonne is Argonne National Laboratory outside of Chicago. Oak Ridge, ORNL is Oak Ridge National Laboratory in Tennessee. There's DOE projects, Department of Energy projects that we're a part of. And then there's a lot of different collaborations that we have with outside groups. And in fact, actually, this is not really a complete list, but it's what fits on the slide and the sort of stuff that we're proud of doing. And we're very happy to be working with some of these people. And it's a lot of fun for us, which is sort of why it is I'm here, because it might be fun to work with you guys, too. OK, so now I want Thomas to talk.
Change the laptop.
Yes.
Don't? Okay. So let me start with telling you why I'm here. I got hired 2 months ago into the Lawrence National Livermore Labs. And my research interests are reverse engineering and program visualization. So the question is, why did I get hired into a compiler group? So the answer is, of course, that Dan and the group, they're interested in analyzing software. So they are interested in reverse engineering and especially using ROSE. So let's introduce you to a framework that I brought from Sweden, where I graduated before, which is the visualizer, which allows you actually to look at source code. So what you do is you have your software system, you have your platine, and you put different chips on that framework. So for example, a chip for retrieval. So we put here rows onto this, something for analysis, and something for visualization. And finally, you get some images in order to understand your software system. So for those of you who don't know what reverse engineering is, I would like to explain it to you. Let's say you have a software system that you've used for many years, and somehow the system gets a little bit strange. So, for example, you discover a bug, and that bug, when you fix it, it leads to the fact that there's many more bugs in your system. So something happened over the years. Maybe you have employed some students for a short time, or I don't know, whatever happens in industry. So what you want to do is you want to re-engineer your system. In order to do that, you need to understand your system. So you put different levels of visualizations of your system. So you try to see at the source code, at different components, and at the entire architecture. To get an image of your software system, you have to perform reverse engineering. So why would you reverse engineer a system? Well, maybe you have noticed that most of the time when you actually try to do changes or enhancements of your software system, most of the time is spent on understanding the system. So for example, for a correction task, you will spend 62% of your time just to try to understand your own system. That means your own system or the company's system, if there's many more developers on that. In general, for maintenance tasks, you spend 40 to 90% on understanding the system. How much is maintenance compared to the entire software lifecycle? Software maintenance takes 40 to 80%, 50 to 80%, sorry. So in the worst case, how much time do you spend to understand your software system? In the worst case, you spend 72% of the software lifecycle to understand your software system. So if you have a software system that lasts for about 10 years, you spent 7 years to understand your software system. Isn't that a waste of time and money? So what we would like to do is we would like to use some kind of tools that help you to understand your system. So what do you take? You take whatever is available of your software system. The source code, the developers, if they're still in the company, and documents. Do you trust everyone? Do you trust the documents? Well, in Germany, they usually trust. I'm German, so I can say that. In Germany, we trust our documents because they're well designed. But in general, you take your source code and you try to produce different images and try to get the idea what happened to the software system. In order to do that, you use a tool. This tool starts by parsing the entire software system. So by parsing the software system, you get a model. Then you try to perform some analysis, and finally you try to visualize to get an understanding. Now, I would lie if I tell you there's only this one tool available. There's many tools available. So especially depending what kind of visualization do you want to have. Everyone needs a different kind of visualization. Maybe you like UML diagrams. So you would put here rational rows or something similar into this place. But it's of course hard if you have rational rows here and you have front end like rows, C++ front end, and you combine them. It might take you a few months, and then you figure out, oh well, I actually need a different kind of visualization. So then you start screwing on that system, and it takes you time. So what you would to do rather is to compose those kinds of reverse engineering tools. So you take just the components that you're interested in for visualization, retrieval, and analysis, and you just create your own individual program understanding tool within hours or days. So that's actually what the visualizer is, and you see here an example of an instantiation of different kind of chips that are put on the platine for retrieval, analysis, and visualization. Now, what can you do with that? An example would be to show a static picture of your software system. So this image is the visualizer itself. It shows you different components of the system. So this is the visualization part. there's some game engine, there's the core, and there's a Java front end, for example. And what you see is the different classes, a call graph between the classes. You have the size of the classes as the size of the spheres here. And what you can see is that the system is very nice decoupled. So you get an idea about the quality of the system. To give you a comparison to a former version, I have to tell you the software system was not always as nice as here in this version. So in 2002, the visualizer itself was very complex. So we had one huge big system. And the red color actually indicates the amount of documentation. So it was very bad documented. Then we had some students working on their master thesis. And finally, after some work that I had done, we got also this picture that you've just seen in 3D, where we have decoupled system, and it's much easier and faster to make changes and understand your system. What else can you visualize? For example, you would like to have an idea about the quality of your software system. So with a visualizer, you could easily arrange different quality aspects of your system into the axis. So let's arrange the complexity of your software system in the x direction, the lines of code in y, and you immediately figure out which ones are the outliers of your system. And not only that, you also figure out who did this huge classes and the complex classes. You might want to talk to that person. Why did you do that way? In the z direction, we have aligned the lack of documentation in the system. So the parts of the code in the front here, they are very bad documented. What I've done in a course is also ask the students to try to different metaphors. And here you see a city metaphor. So what you see is different classes represented as buildings, textures showing the same as the height, the amount of lines of code. And then you have the quality presented as a texture, a fire texture, showing you bad quality of the software system. And the more it's burning, the worse it is. And if your entire city is burning, you probably should do something about your program. Okay, so the purpose of reverse engineering is, of course, to understand your software system much faster and better, save time and money. What would you like to see? You would like to see the code structure, ideas about the quality of your program. You want to find code duplicates. You want to see if there's any malfunctions. Have these malfunctions been introduced by purpose or not? And maybe the managers would like to see the work distribution or progress that you can also measure over a certain time. So what I presented you right now is the visualizer, and the visualizer is going to be, or is already working together with Rose. And the future work that I'm working on is to find interesting patterns in million lines of code of C++. But I don't have any results so far. But if any one of you is interested in that work, please come and talk to me. Yes?
So there's a company, I think, called Clockworks, and they have a tool called Code Surfer or something like this. It sounds very similar. It's been out for a few years. Can you comment on what the differences are?
I know a tool called Code Crawler from Switzerland. And I know a German company which is having a similar tool. But compared to the framework allows you basically to put different tools together very quickly.
We're really not trying to present products. And so we're not really trying to compete with products.
Sure, but if something's already been done before and it's been commercialized and all that, why?
No, the problem is that if you have a commercial tool, like I know one German tool, and they sell a license for $50,000 or something. And the problem is, if you come up in a year with a new kind of visualization or a new kind of programming language and so on, you will have to spend a lot of time into getting this tool to get the new features. While if someone creates a new visualization that is interesting, you can put it in within hours into this framework. So that's the difference.
Yeah. Actually, the question about Rose, maybe I missed this, but how is licensed, Rose licensed?
Rose is open source. All that we do is open source, and Rose is released under BSD license. It's not released on the web yet. We've given it out to about 24 different groups that we collaborate with internationally, but it'll be released this summer. I'm be happy to give you, access to the full documentation. There's about 15 megabytes of documentation in a package which I could easily give out. It's been reviewed and released internally at the lab. They actually made me a reviewer because I didn't want to read it, but it's a huge amount of documentation, and it represents all of our documentation for Rose. What you're seeing in the tutorial is one of 3 pieces of the documentation. There's also a manual, and then there's also all of the HTML web pages which document how the classes are used for the intermediate representation.
Do you know how much EDG charges for a full license?
$50,000 to $250,000. Probably they charge me less than they charge you. But basically, for research use, there's no problem. We can give out a binary. So we routinely deal with the IBM guys with by giving them a binary, and we'll make rows available with binaries. But there's nothing that we really modify of EDG, so it's not really a big deal for us to move up to newer versions of EDG, et cetera. But we're, of course, very thankful that they have this sort of research license program, which allows us access to it.
Do you know the restrictions on that research license?
Yeah, for research only. we may at some point decide to actually buy a license. I don't know, but we'll see. Then we would remove all restrictions, except that we couldn't distribute their source code. But we'll see.
Well, thank you.
Thank you.